So let's talk about the cardiac cycle. And this is the repeating pattern of the heart pumping, right? So there are two, I guess, phases of the cardiac cycle. One's called systole, and this is basically the contraction of the chambers. And the two atria contract at the same time, and then the ventricles contract at the same time. So you have atrial systole, and there is ventricular systole. And when the chambers are in their relaxed phase, that's called diastole. Heart chambers. And so again, you can have atrial diastole and ventricular diastole. So the way that the blood moves from one chamber into the other is just through changes in pressure. So while the ventricles are relaxing or they're in diastole, the blood will flow. I'm using this kind of imaginary heart here. They'll flow from the atria into the ventricles just kind of because they open up, and like if you did the same thing, if you I don't know, opened up a bag and water or air or whatever would flow into that because of the low pressure. Let's say between the chambers. So, for example, during ventricular diastole, about 70% of the blood that's in the atria just naturally flows into the ventricles, just due to the pressure changes. And then the remaining, like 30%, is, let's say, forcibly pushed out when the atria contract. Right? So during ventricular systole, or systole, what happens is the ventricle contracts and it causes the AV valves to basically slam shut. AV valves is atrioventricular valves, so this is the bicuspid and tricuspid valves. So the AV valves slam shut, the papillary muscles contract. I always misspell papillary. And that hold the chordae tendineae in place, or hold the flaps in place via the let's say AV valves shut via the chordae tendineae. And then the blood is pushed out through either the pulmonary circuit or through the systemic circuit. And at the same time, the atria are going through diastole. And then they begin to fill with blood. For the next, step of the circuit. The next, I guess, circuit stage. I guess I'll call it. I don't know. Cycle. There we go. The next cycle. Physiologists have come up with the most ridiculous sounding name for the sounds that the heart makes during the cardiac cycle, and they call it either lub-dub or lup-dup. Lub-dub, lup-dub, lup-dub. And so the lub part of it, the first kind of bump that you hear, this is ventricular systole. And that sound that you're hearing are the AV valves slamming shut. And it's so forceful that basically the valves shut suddenly, and then it causes kind of an echo to go through the blood. So it's not the actual heart pumping that you're hearing, it's the sound of the valves slamming shut. And then the dub is the sound that happens when the ventricles go into diastole and the semilunar valves are slamming shut. Semilunar valves slamming shut. Okay. So again, it's not the sound of the muscle contracting. It's not the heart itself is not making the sound. It's the sound of the valve slamming shut and then echoing through the blood. So all of this is these actions that are going on with the heart are controlled through what's called the cardiac conduction system. And as I'm sure you remember, heart cells are cardiac muscle cells. Connect to one another through intercalated discs. Okay, so when you reach, or when the end of a heart cell is reached, it connects to another one through this special structure called an intercalated disc. And if you remember when we talked about action potentials, and when neurons get down to the synapse, they have to do like kind of a hop, I guess you would, down to the next neuron. the neurotransmitter is released and it's got to reach over here, and then that causes the next one. Well, because these are connected via this intercalated discs, they basically act like one cell. Okay, and that's good because we want the heart to fire rapidly and act as one complete unit, right? So, what this forms are these regions called functional syncytium. Make sure I'm spelling this right. Yes. They're masses of merging cells that act as one unit. Okay, so there might be, I don't know, millions of cells, but they act as if they're just basically one cell. And in the heart, there are two. The atrial syncytium. So basically, the two atria act as one unit and contract together as a unit. And then likewise, the ventricles contract at the same time too. So they're known as the ventricular syncytium. The two ventricles as a unit and therefore contract at the same time. Same time. So think about if they did not, then you might have atria, ventricle, atria, just let the part just go bump, it'd be like a mess, right? But you want it to go atria, ventricles, lub, dub. You need the heart to act as a unit. Otherwise, it's just gonna be a mess. Okay, so that was kind of a step forward. We're going to go back now to the cardiac conduction system, which is basically the signal that tells the heart when to contract. This basically coordinates the cardiac cycle. So there's a special mass of cells that is up in the right atrium, or in the wall, I guess, of the right atrium, called the sinoatrial node. Most people just call it the SA node. And it's also known as the pacemaker, because this is where the conduction starts. Pacemaker. So this is a mass of cardiac muscle cells in the right atrium wall, where the signal basically starts. And sometimes, like in Indiana Jones or movies, they'll like cut the heart out of someone and it'll still keep pumping even though it's outside the body. It's because the sinoatrial node, or the pacemaker, basically sets the pace of the heart, and it acts independent of basically the brain telling it what to do. So it has this kind of intrinsic, with a intrinsic, call it rhythm. And it's a little complicated beyond the scope of the class, but basically what happens is it's able to remember we talked about in the nervous system that if you did not reach threshold stimulus, the nerve wouldn't fire. Well, the heart has this kind of leaky kind of pattern to it, and basically it allows it to depolarize on its own. Intrinsic means kind of like built in. So that starts the cycle. Okay, so when the signal starts, it's basically going to run, real simple heart here. We're going to have the SA node is going to be somewhere up here, and then the signal is going to be sent to the two atria, and that causes the atria to contract at the same time. The atrial syncytium and then the atria contract together. Okay, then the signal keeps going. To the, wrong color. An area called the AV node. And that slows atrioventricular node, also known as the AV node. And then the signal slows down. Okay. Then the signal is going to go through these special cells, or not, let's just call it special tissue called, I'm gonna run out of room. Signal follows into the, what are called the Purkinje fibers, I believe is how it's pronounced. Signal follows so I always, the Purkinje fibers, I always assumed that Purkinje, it sounded like an Indian name, and it was probably named after, some Indian physiologist. Turns out that it's actually a guy from, I think it was like Sweden or Denmark or something, so it's probably more like Purkinje. But anyway, this is in the atrioventricular septum, so the signals basically go down the atrioventricular septum, and then they go up the walls of the ventricle. So I'm just going to kind of flash forward here. The signal, when it goes to the Purkinje, or however you say that name, it speeds the signal back up. And then the signal reaches the ventricular syncytium, and the ventricles contract. And the ventricles contract. Ventricules. That's not how you spell ventricle. Wow. Coronavirus. The side effects of coronavirus: when you don't have it, your brain turns to mush. So what this basically does is it allows the heart to beat in that pattern that we want it to: atria, ventricles, atria, ventricles, atria, ventricles, to contract like that. If the signal didn't slow down and then speed back up again, it would be atria ventricles, atria ventricles, atria ventricles, and the blood would just basically get pushed nowhere. We need to push it from the atria down into the ventricles, and then back out the ventricles, and then into atria, so that it it flows in the right pattern, right? And this slowing down allows that to happen. Okay. So we can measure the electrical changes that are occurring within the cardiac cycle through a electrocardiogram. Otherwise known as an ECG. You may have seen it or heard it as an EKG. I'm assuming it's the Germans. They spell cardio with a K, cardiogram. So we speak English, so ECG. This is a recording of the electrical changes. Electrical changes in the cardiac cycle. And so you can use an ECG to figure out, or maybe you and I may not be able to, but people are able to. It sounds very complicated, but you can use these readings to figure out what part of the heart is not behaving or contracting or whatever properly. So on the y-axis you have millivolts, the change in electricity, and here you have time. And so let's just kind of start here. You've got a bump and then a bump, 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 bump. Okay, that's one cardiac cycle. This first little bump here is called the P wave. And the next is called the QRS complex. And then finally down here you have the T wave. So the P wave, it represents the depolarization and therefore the contraction of the atria. Okay, so then you're basically here, what you're talking about is atrial, not arterial, atrial systole. Okay. Then in the QRS complex, this is the depolarization. QRS complex. It's the depolarization of the ventricles. Okay, and therefore ventricular systole. And then this last one down here, the T wave. This represents the repolarization. So the repolarization of the ventricles, and therefore ventricular diastole. And I know you're very astute and you're thinking, wait a minute, when do the atria repolarize? Well, they do repolarize and relax, but it's hidden this is such a strong signal here that it's hidden behind the QRS complex, so you don't really see it on an ECG. So ECGs can be used to diagnose heart problems. Say specific heart, let's say, issues. So if you see an irregular QRS complex, then you know there's something wrong that's happening during the depolarization of the ventricles versus in the P wave. And I'm not really, like I said, great at drawing these, but I mean, one easy way is, or one easy thing you can do is I mean, obviously that's a problem with heart rate, because it just goes bump, bump, bump. Or likewise, if these were really pushed in together, then you would have what's called tachycardia, where you have your heart's going bump, 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 bump. And there are all sorts of different, something's going on there, right? That's probably a heart attack. So, yeah. So, blood flow obviously is going to change depending on your activity levels. Let's say the O2, well, I guess not just O2, O2 demands of the body, and then the getting rid of carbon dioxide, O2 demands of the body. So, say during exercise, you're going to need more oxygen getting out to the body. So the heart rate's going to increase, as well as other physiological changes that we'll talk more about later. But the heart rate can be adjusted. Like I said, there's this intrinsic, a sort of built-in rhythm to it. And if you need more, you can just tell the heart rate, hey, increase. Or if you want it to relax, you just, we'll talk about that in a second. The SA and the AV nodes are controlled or stimulated by parasympathetic, controlled by parasympathetic and sympathetic divisions of the autonomic nervous system. As I know you remember. So the parasympathetic stimulation, it will slow the heart rate down. HR, heart rate, slow the heart rate. Or if you turn off stimulating the parasympathetic, or if the parasympathetic stops, then the heart rate will just naturally increase on its own, right? The sympathetic, remember, that's the fight or flight, so you need more blood, you're going to need more oxygen. All these things kind of ramp up. Too many eyes in there. The sympathetic division is going to increase heart rate, of course, and get you ready to outrun lions and tigers. There are also parts of the brain. Cardiac control center. course, you remember that's in the medulla oblongata. Medulla oblongata. Oblongata. So there are what are known as baroreceptors. Baro meaning pressure in your some of the blood vessels. Baroreceptors. They sense blood pressure changes and then send that signal up to the brain to tell it to, okay, let's slow the heart rate down or let's speed it up. Blood pressure changes. There are also parts of the cerebrum and the hypothalamus. So this all has to do with regulating the heart rate and the cardiac cycle, right? The cerebrum and the hypothalamus. They can have an effect. Hypothalamus. So if you're emotionally distressed, guess what? Your heart rate goes up. On the flip side, if you faint, well, then your heart rate will decrease. Okay. It's controlled by those parts of your brain. There are some well, I guess this isn't really external, but your body temperature will affect your heart rate. So if you're hot, or your warm body temperature, that causes an increase in your heart rate. And if you have a low body temperature, that's going to decrease your heart rate. And I'm pretty sure we talked about hypo and hypercalcemia, but there are some effects that ions will have, in particular potassium and calcium. So if you have, how do I want to do this? High potassium, so let's just put here. If you have high potassium, this is called hyperkalemia. Hyperkalemia. And if you have low potassium, you have hypokalemia. And the effects of this, I'm going to put this in a different color. You will have a decrease in the heart rate and a decrease in the force of contraction of the heart. If you have hypokalemia, this can cause arrhythmia, which is a unusual, or how do you word this? Arrhythmia, not standard heart rate. Arrhythmia. So this can cause what's called bradycardia, or a low heart rate. Bradycardia, which is not less than or greater than. Your heart rate drops below 60 beats per minute, BPM. On the flip side, if you have arrhythmia, this can cause tachycardia. Which is greater than 100 beats per minute. Okay. And calcium, if you have high calcium, then you have hypercalcemia. So I'm going to draw a line here. And hypocalcemia. And what can happen with hypercalcemia, this will increase, let's just say, increase the heart rate and extend the contractions so that the heart contracts for longer than it needs to. Extend the contractions. And then this over here basically can just decrease the action of the heart altogether. And there you have it. See you in the blood vessels section next.